So today we are starting the stereoisomers, and under this we are going to do the optical isomers. The geometrical isomers is also belongs to the stereo. So I already uploaded the video about the geometrical isomers. So I suggest that you have to revise the geometrical first and then come to the optical isomers. Let's start. So optical isomers, just like name, it is related to the light, and isomers means molecular formula same but the structure is different in 3D. So what is exactly is happening here in optical isomers? We are taking the ordinary light which is propagating in all direction. This ordinary light we are passing through the Nicol prism, which is the polarizer. What it can do? It can convert this ordinary light into the PPL, means plane of polarized light. Now this PPL we are passing through the organic sample. We can take a tube of L length, filling with some concentration of the organic sample. We can observe the three possibility. The one possibility, no change in the light. If no changes happen with the PPL, we can say it's an optically inactive compound. If clockwise rotation happen, we can say it's optically active. If anti-clockwise rotation happen, then again we can say optically active. For clockwise rotation, we can keep the name that is called dextrorotary. The symbol is D or plus we can use. This is levorotary. The symbol we can use L or minus, and they both are the optically active. These two are optical active. Now the some rotation we are getting here, that is called the theta degree. This theta I can write as an observed rotation. Now if this observed rotation has happened some particular condition, like the concentration of the solution, if we are taking 1 grams per ml and the length of the tube has been taken 1 decimeter, temperature if we are keeping 25 degrees Celsius, and the light wavelength around 589 nanometer, then in that case we can say the specific rotation. Otherwise the specific rotation would be is equal to observed rotation by concentration and the length of the tube, where the concentration will be is equal to, it should be grams per ml and L should be in the decimeter. So based on that, let's do one question. So like here we have a question, observe rotation of 2 gram of organic sample in 10 ml solution in polarimeter tube of 25 centimeter is 13.4 plus. So we have to find out the specific one. So we know that specific should be is equal to observed by C into L. You have to take care of the unit. Plus mean it's a dextrorotary. Concentration is a grams per ml, so this is 2 and 10. Unit is fine, so 2 by 10 grams per ml. Length should be in the decimeter. Here it is given centimeter, so we are going to convert into the decimeter, 25 by 10. So when you calculate everything, you will get plus 26.8 degree. Pluses represent dextrorotary, and that's how we will get the specific rotation. And this entire setup is named as polarimeter. Now the question rises, how we can see that molecule is showing the dextro and levo, means how they are rotating the plane of polarized light in clockwise and anti-clockwise. So in 2D, means in plane of paper we are checking few conditions, and these conditions are, so first one is no plane of symmetry. The molecule should not have the plane of symmetry. What is the meaning of symmetry? Like for example, if I have a cyclopropane, and if I try to cut like this way, the first part and second part is become same. It means it has the plane of symmetry. If I try to draw the D, let's say example, if I put D, if I cut in the middle, it has the plane of symmetry. But if I do P and try to cut any plane like horizontal or vertical, I am not getting the plane of symmetry. So the short pattern is POS. The molecule should not have the POS. Second condition, the molecule must have chirality. Chirality or chiral center means no symmetry, or else you could say the molecule should be asymmetrical. So like for example, if we have a carbon, this is held by the different substituent, like for example hydrogen, here is a methyl group, here is deuterium, here is a CHO group. All the four substituents are different, that atoms and molecules all are different around it. So we could say this molecule is fully asymmetrical, means it has the chiral center. And the chiral center is this, represented by star. The chiral center should be the sp32. But if I draw like that way, let's say hydrogen, hydrogen, methyl, methyl, you could say it has a symmetry. If I draw the plane of symmetry from here, we can get the equal parts. And the four substituents also not different, so we can say it's a symmetrical molecule, it's a chiral center. So technically we need a no plane of symmetry and molecule must be chiral, means fully asymmetrical center we needed. The third condition we have, no center of symmetry. What is the meaning of center of symmetry? Like suppose we have a molecule, this is the center. Now I am going to put hydrogen, chlorine, hydrogen and chlorine. Now we have to draw the perpendicular from the center. अगर ये यहाँ से डालोगे तो equal opposite distance आ रहा है, means it has the center of symmetry. If equal and opposite distance is not there, it doesn't have the center of symmetry. इसको लिखते हैं COS. For example, मैंने cyclobutane फिर से draw किया. There is a chlorine, there is chlorine. Now they are not diagonally opposite from the center. See, this distance are different. The center of symmetry means diagonally opposite, so it doesn't have the COS, but it has the COS. I can check the plane of symmetry too. If I am drawing like that way, the first part and second part is same, so we could say it has the POS like this. And here if I am drawing like that way, so this part and this part both are same, so I could say it also has the POS. So if any molecule have the plane of symmetry or center of symmetry, means it's optically inactive. So no plane of symmetry, no center of symmetry, must have the chirality. And the fourth optional condition, that is called excess of symmetry. Excess of symmetry might, like for example, carbon is a tetrahedral, hydrogen, hydrogen, this side hydrogen. So if I try to rotate this hydrogen, holding here and rotating, every time we can see the hydrogen in front of us, मतलब उसके पास excess of symmetry है. तो किसी भी rotation में if the excess of symmetry is appearing, means molecule is inactive. Ultimate condition कौन कौन सी है? We have to check it that no plane of symmetry and the center of symmetry. The chirality is again telling us the molecule does not have the plane of symmetry. So these condition is necessary to find out that whether the molecule is showing the optical isomers or not. Now let's do some question based on that. So like for example, now we have a question, we have to identify how many chiral we have, the asymmetrical molecule. So here in the first one, if you see, the chiral should be the sp3 hybrid and must have the different substituent. So this carbon is chiral, which is represented by star. Hydrogen, iodine, bromine and chlorine, all four are different, it's chiral. Let's check with this carbon, hydrogen, OH, deuterium and the bulky group, this is also chiral. Even this is also chiral, iodine, fluorine, bromine and the bulky group. So both are the asymmetrical one. Let's see this one. So we have a hydrogen and hydrogen is same, it's become achiral or symmetrical. Here in the ring compound, what we can do, we can opt any carbon like this carbon, chlorine and here hydrogen. Let's draw the perpendicular. The both part is same. If the both part is same, it's become achiral, means symmetrical. But here if you see, if you draw the perpendicular, that first part and second part is different, and here chlorine and hydrogen, all the four substituents are different, so this is chiral. Even we can observe this is also chiral. Why? Because here the methyl group we have, here hydrogen, and if you draw the plane of symmetry from here, that first part and second part is different. It shows that this center is also chiral. Even here this carbon is a chiral, because if you draw the plane of symmetry, here the bromine is different, hydrogen, first part and second part both are different, so this is also chiral. So among these only this one is achiral, rest are chiral. This is also achiral, this one. So in this molecule we have again question, we have to identify how many chiral carbon we have. So here this carbon if you observe OH and here is a hidden hydrogen, if you draw the plane of symmetry, the first part and second part is different. So this is chiral, even this is chiral, having the different section. This is CH2, both hydrogen is same, so not chiral. Even this is CH2, the two hydrogen are same, not chiral. Now this is chiral. You have a bulky group, you have hydrogen. If you divide by putting the perpendicular, both the section are different. Oxygen is not chiral because two lone pair same, and anyway question was chiral. This is chiral. You can see both the sections are different. This is chiral, even this is chiral, this is not chiral. So total how many chiral we have? 1, 2, 3, 4, 5, 6. 6 center we got it, the chiral one. Hope you got it. So I'll give some questions here, that is as a homework you can do. So in this question you have to identify how many chiral or the asymmetrical molecules we have. You can count the number of chiral also, like here how many, here how many, and let me know in the comment box. Now we have some important term in optical isomers. The first one is called enantiomers. So enantiomers are optically active compound, stereoisomers whose mirror image are non-superimposed. So what is the meaning of the non-superimposed? Like suppose if the A mirror image is A and you are keeping A exactly on it on 0 degree and 180 degree, it will superimpose. But B mirror image, if you try to keep exactly mirror image on this, it cannot be the superimpose. So we could say that optically active isomers should be the non-superimposed mirror image. So obviously they don't have the plane of symmetry. And they can rotate the plane of polarized light in clockwise and anti-clockwise direction. So example we have lactic acid. So if I put the lactic acid, it is HOH, COH, CH3 group. I'll make the mirror image of this COH, OH, CH3 and H. And these two are the chiral, it doesn't have the plane of symmetry. So if I try to keep this mirror image on it exactly on 0 degree or 180 degree, it cannot be superimposed. So we could say it's a non-superimposed mirror image. One can be dextro, other could be levio. If suppose this is dextro, the mirror image will be levio, and these both are named as enantiomers pair. So we could say dextro and levio pair named as enantiomers pair. Here the very special point we have to add up racemic mixture. So racemic mixture means equal molar of dextro and levio mixed together. Equal moles of dextro and levio in aqueous solution form racemic mixture, which is optically inactive. Talk about separately for the dextro and levio, they are considered as an enantiomers pair. But if you take the equal molar concentration of dextro and levio in solution, then whatever the dextro rotation is there, it get neutralized by the levio rotation and form the racemic mixture, which is optically inactive. The next terminology is coming, that is called the mesomers. So mesomers are those compound or those stereoisomers which are optically inactive due to plane of symmetry, POS. So like for example, I am writing the tartaric acid. We have a COH, we have COH, HOH, HOH. So if I am checking the chiral center, it has the chirality here, it has the chirality here, but it has the plane of symmetry too. It is dividing into the equal ratio. So due to the POS, it's become optically inactive compound. So remember that mesomers must contain the minimum 2 chiral center with the POS. If it is there, these are the stereoisomers but optically inactive. Third is coming, that is called diastereomers. Diastereomers is another term. This is non-mirror image of each other. So like a molecule which has the chirality, no matter have the plane of symmetry or no plane of symmetry, but if they are non-mirror image of each other, considered to be the diastereomers. So I'll take an example of tartaric acid itself. Let's say the first one I'll take, which here this one I'm writing HOH, HOH, and now I'll write the different image of this OHH and HOH. You can observe that first one is not a mirror image of the second one. So we could say these are the diastereomers pair. They may be or may not be optically active, but obviously they are stereoisomers. So now we are going to do the RS nomenclature, which is helping us to identify which is dextro and which one is levio. So polarimeter is another method to find out the dextro and levio in the laboratory, but RS nomenclature is helping us to find out on the paper. So in the exam you have to use the RS nomenclature. R is stand for the rectus and S stand for the sinister. It's telling us it's a clockwise rotation and this is anti-clockwise rotation. And it is based on the CIP rule. This is rectus and sinister. Now it is based on CIP rule, and CIP rule is based on the atomic number. If the number is same, then you can go with the atomic masses too. So the full form of the CIP rule is called Kohn in gold pre-log rule, and it is based on, we could write atomic weight. You can check atomic number as well. So if the number is same, you can go with the atomic weight. We already used this CIP rule in the geometrical isomerism for finding the E and Z nomenclature. So I am going to use a similar pattern to find out the rectus and sinister, means clockwise rotation and anti-clockwise rotation. So like for example, if I am taking a chiral carbon which is connected with fluorine, chlorine, bromine and hydrogen, we have to identify whether it's optically active or not, or if it is active, it's a clockwise rotation or anti-clockwise rotation. So we can observe here it's a chiral center we have, and now we can give the priority to these halogens and hydrogen. So based on the atomic number or maybe mass, the bromine is getting the first number, then chlorine, then fluorine, and the fourth position is hydrogen. Now the rule is telling if the least priority group present on the vertical line, means the 4 number, if it is present on vertical line, then you can start moving from 1 to 2, 2 to 3 like this way, and this is happening in the anti-clockwise pattern. Anti-clockwise pattern means the configuration is become S. It's a levio rotary, consider. Let's take the mirror image of this. We have fluorine, chlorine, bromine and hydrogen. So we can observe the mirror image obviously have the chiral center. We can give the number 1, 2, 3 and 4. The least priority is coming on the 4th position, and that is on the vertical line. Now again we start moving from 1 to 2 to 3. So if we are going from like this way 1 to 2 to 3, then it is happening in the clockwise manner. A clockwise means it become R. So remember that the S mirror image is always R and R mirror image is always S, means one should be dextro and others should be levio. Clockwise, indirectly we could say it could be dextro, and S means it could be levio. Let me take one more example. If we have COH group, CH3 group, OH group and deuterium. Now CIP rule is telling we have to compare these based on atomic weight. Now here we have a carbon. Okay, don't take the total one, we have to go one by one. This is also carbon, this is oxygen connected, this is deuterium. So between carbon, oxygen and deuterium, oxygen is the heaviest one. Then we have a carbon and here we have a carbon. So let's move to the next one. We give the priority to the multiple bonded. So here carbon is held by the double bond by the oxygen. So if the double bond is appear, 2 times double oxygen you have to count. Obviously this become heavier and this become lighter, and the least priority is still coming on the 4th position vertical line. Now let's move 1 to 2 to 3. It's clockwise pattern. Clockwise means it's become R rectus. And if I draw the mirror image of this, it's become COH, it's become CH3, this become OH and this become D. So by default the answer should be S. And let's cross check it. This is first number, this is second number, this is third number and this is fourth number. So we will get the anti-clockwise rotation and that should be S. So these were the case where the least priority present on the vertical line. Now I am writing the least priority on the horizontal line. Case 2. Least priority group on horizontal line, where this was the case 1, where we wrote it least priority on vertical line. So least priority on the horizontal line, let me put the value. Here the chlorine, bromine, hydrogen and fluorine. Now you can observe the hydrogen, I put it on the horizontal line, and based on the comparison CIP rule, this is number 1 heavier, this is lighter, and then is the third number, and this is the fourth number. Now let's move 1 to 2 to 3. It is happening anti-clockwise, so it become S. Okay. So when the least priority coming on the horizontal line, the R configuration convert into the S, and S configuration will convert into the R. So here we got the S answer, so it will convert into the R. And if I write the mirror image of this, obviously answer is become S. So now the rotation is started. This is 1, 2, 3 and 4. Horizontal line 1, 2, 3 clockwise. So it become R, but the answer is become S because rotation we change. So these are the two cases where we have to apply the RS nomenclature. Now I am writing few more example. I am drawing 2D structure that is called Fisher projection. So these all structures are considered as a Fisher projection. COH, COH, HOH, HOH. I'll write another configuration of this molecule. It's called tartric acid. Then I'll draw the mirror image of this. I'll draw the mirror image of that also. So let's do it RS nomenclature of the tartric acid. This carbon is chiral, this carbon is also chiral, this is chiral, this is chiral. Now let's see, since it has the plane of symmetry, so we could say it's a mesomer. This is also mesomer, but we have to find out the RS nomenclature. So oxygen is number 1, then COH, the bottom side bulky group is number 3, and this is number 4. So we have 1, 2, 3, 4. 1, 2, 3, 4, it's become anti-clockwise. Anti-clockwise means it become S, but it will be R because least priority on the horizontal line. Same thing is here, 1, 2, 3 is there, and the 4 is here. We can move, it's a clockwise direction. Clockwise direction means it become S, but it convert into the, so 1, 2, 3, this is the clockwise direction, means it could be R, but it became S. So if I write the IUPAC nomenclature 3 and 4, so we got it 2R and 3S. So the mirror images become 2S and 3R. Same thing is here, we can apply. Oxygen is heavier, then COH, then the bottom side, and the least priority is on horizontal line 4 number. So if we are rotating 1, 2, 3, it's clockwise. Clockwise means R, but it became S because of the horizontal line having the least priority group. And then we will apply downside also, that is 1, 2, this side is 3, and that is 4. So 1, 2, 3, 4, it's a clockwise direction. Clockwise means R, but it became S. So if I write the IUPAC nomenclature, second carbon have S and third carbon is also have the S. So this become 2R and 3R. So among these two, if I write the number, this is first one, this is second one, this is third, and this is 4. So third and fourth are enantiomers pair due to non-superimposed mirror image, where 1 and 2 are identical. How identical? You can see these are the mesomers, individual mesomers. But if 2R and 3S, and if I start giving number from bottom side, IUPAC pattern, so the second number is become R and third number is become S, which is matching with this. So nomenclature has become same, so that's why it's become identical. However, individually you can say the one is mesomer and second is also mesomer. Where if I write 1 and 3, 1 and 4, these are the diastereomer, non-mirror image of each other. This is also diastereomers. So that's how the RS nomenclature is helping to identify the stereoisomers. Now let's apply this RS nomenclature in 3D structure. Now next point is how to convert the Fisher projection into the 3D pattern. So So Fisher is suggesting, this is the 2D diagram, that vertical line is behind the page, means behind the paper. So I'll write like that way. This is the COH present here and the CH3 is present here. It's a behind of the paper, where the horizontal line is above the paper, like this way. It is also suggesting the highest priority group, we have to keep it on the vertical line on the top side itself. So I'm going to convert like that way. It's become COH top line, and we will write here this hydrogen, I'll write here. So these two group I'll write on the vertical line and OH on the solid line. So I'll put up on the solid line itself. Above the means toward us, and this dash line means away from us. So basically these two group, it should be behind of the page, and these two groups should be toward us, above the page. So we convert 2D Fisher projection into the 3D pattern. Now let us understand how to apply the nomenclature, RS nomenclature. So first I am doing a case where the least priority is present on the dash line. So case 1, least priority on dash line. So like for example, I am writing the lactic acid. We are going to give the priority based on the CIP rule. Remember that CIP rule is based on the atomic number, or if the number is same, you can go with the atomic weight. And if you directly wanted to apply atomic weight, you can go ahead. So here the carbon is a chiral, and this is connected with oxygen, carbon and carbon hydrogen. Oxygen is heavier, number 1. Now carbon common, here the double bonded oxygen will get the better priority than this one, and least priority is coming on the dash line. So if the least priority coming on the dash line, we will follow the vertical line nomenclature. Means clockwise will be R and anti-clockwise will be S. So let's move it 1, 2, 3. This is become anti-clockwise, so it become S. Now case 2, if the least priority is present on dash line, then we will apply the horizontal line nomenclature. If least priority on the solid line, then we will apply horizontal line nomenclature. So like for example, if I go like that way, so based on the CIP rule 1, 2 and 3, and this is 4. So 1, 2, 3, this is anti-clockwise, this become S, but it turned to be R because least priority was present on the solid line. So we flip the configuration. Now if it is present on the normal line, in 2D line, then what is happened? Then again we have to flip the configuration. Like for example, so like this is 1, this is 2, this is 3 and this is 4. Since it is present on the normal line, so our target to put this least priority group on the dash line. So we have to flip 2 times here. So as of now the configuration is 1, 2, 3. It's anti-clockwise. It's become S, but it turned to be R and then S. So if you rotate the even number of times, that configuration is become same. If you rotate the odd number of times, configuration is just get reverse. So these were the cases where we have to find out the RS nomenclature. Now next we are moving, this is the small note, that R mirror image is S, or S mirror image is R, or RR mirror image is SS, or RS mirror image is RS. It should be SR. Then we can say these are the enantiomers pair. But if the mirror image is not 100% reverse, like RS is become RR, RR is become RS, it's a half change, so that is called diastereomers pair. And if the RR mirror image is coming RR, then we can say these are the identical, RS, RS, so these are the identical. So we have some important question about the optical isomers. The observed rotation of plus isomer means any enantiomers is 8.7 degree. Plus is written means it's a dextro. If a specific rotation of mixture of plus isomer and minus isomer is 1.4, find the percentage of plus isomer. So that's a question. So basically it's a question of the optical purity or the X is enantiomers. That is why that resultant having the plus 1.4 degree. So optical purity would be is equal to the observed one means 1.4 of the solution divided by the original one. Original how much? 8.7 into 100. So when you are calculating this, you will get the 16%. So 16% is the optical purity. So amount of optical impure is 100 minus 16. it become 84%. So 84% is an impure, so we could say it's a racemic mixture which is optically inactive solution. So if we talk about the total positive enantiomers, isomer or maybe the enantiomer, the dextrorotary enantiomers, we would have 84 half was present, that is the dextro, and the how much is present, 16 is also there. So total we got the 58%, that is the X-cis enantiomer. Next question, we have the specific rotation of leviorotary 2-bromo-octane is minus 36 degree. What is the percent composition of the mixture of enantiomers of 2-bromo-octane where rotation is plus 18? Rotation plus 18 means it is going to the dextrorotary. So for this thing we will apply a formula that is called mole fraction. So mole fraction for dextro plus mole fraction of levio, that should be is equal to 1. Mole fraction dextro, mole fraction levio, that should be equal to 1. And we can write the, based on the rotation, we can write its optical rotation would be is equal to mole fraction of dextro, the rotation of dextro, plus mole fraction of levio, rotation of levio. So this is given plus 18. So we'll put the value here. This is the 18 is given in the question. And dextrorotary we have to find out, and leviorotary minus is given. So that should be minus 36. So let me put the value. This is automatically will be plus 36 because same enantiomers we have. So calculation is 18 should be is equal to dextro into 36 plus 1 minus dextro minus 36. So when we are calculating this, the mole fraction is coming 1 by 4. So we are getting this is 3 by 4 means around 75%, and for levio we will get it 1 by 4 means 25%. So racemic mixture we have, that is 50 plus 50. So we will get the racemic mixture 25% levio plus 25% dextro, that we will get the 50% of racemic, and rest is dextro is higher, so the optical rotation is showing the plus. So overall nature is a dextrorotary of the mixture. X-cis enantiomers will be is equal to, that is 50%, because from here 25% got neutralized and rest of the 50% is left behind. Now next question we have, identify the number of chiral carbon in the following. So we have chiral here, all the 4 substituents are different. Here it is, this one is not, methyl same, and it has this one is here. So all 3 have the chiral carbon. Next question we have, number of possible isomers of glucose. So the meaning of the CHOH whole 4, HOH, HOH, HOH and HOH. So we can observe there are 4 chiral center we have, 1, 2, 3 and 4, and asymmetrical molecules, so 2 to the power 4 means 16 isomers. So answer should be 3. Now the final thing is coming, how to calculate the total stereoisomers. So stereo, as we learned it, it's a part of the geometrical and optical. So if I talk about the stereo center, it can be sp2 and can be sp3 as well. sp3 is a chiral and sp2 where the JEE is possible. So the formula, number of stereoisomers for asymmetrical molecule is 2 to the power n, where n is stereo center. So like for example, if the question is coming, find the stereoisomers for this molecule. So this double bond is showing the geometrical isomerism. This is chiral, so total stereo center is 2. Your answer should be 4. So we have R and cis and R trans, S cis, S trans. These are the total 4 possibility. So in this case we have to identify how many stereoisomers we have. So we have this chiral, this double bond where the JEE is possible. This is the chiral and this is also chiral. So total we have 2 to the power 4 means 16 isomers we have. For more updates, follow Chem type. We already done the geometrical isomers and structure isomers. Don't forget to revise first before the optical isomers. Next video is a conformational isomers. So stay tuned and keep watching. Thank you.